Okay, so today we are interested in learning or finding out how you work out the resultant force. The reason why we are interested in resultant force is because according to Newton's second law of motion, it is this resultant force which determines the acceleration of an object of mass m. So the acceleration depends on the resultant force, whether the resultant force is there or not. And we are interested in finding out about the resultant force along the x direction and along the y direction. Now, resultant force is a vector. That means that you need to add vectors together, or you need like that along a particular direction. The direction of interest is the x direction or the x-axis and the y direction. So the x-axis is basically your horizontal direction and your y-axis is the vertical direction. So we will start with the case of our box, which is on a horizontal surface, this box. So we want to find out what is the resultant force on this box along the horizontal direction and what is the resultant force along the vertical direction. As you can see, in the horizontal direction, there is this force F which is pulling the box this side. So that is a pulling force, F. Since the box is going to move this particular direction, that's what we are assuming, that the box will move in this particular direction, there is this force, FF, which is a friction force, which is going to oppose the motion of the box in this particular direction. So for this box along the horizontal direction, we identify two forces, the pulling force F and the friction force which will oppose the motion of the box. In the vertical direction, the y direction, the box has got mass m, and since the box has got mass m and this box is on earth, then it means that this box has got weight. So this box has got weight, which is the weight we are seeing here, Fw. This weight is directed downwards. So this box exerts a weight, Fw, on this flat surface. This flat surface is not going to sit idle. It will be unhappy about this development. So it's going to push back against the box. Equal and opposite using this force, which is the normal force. So even in a simple case like this, where we just have a box lying on a flat surface, there are a number of forces acting which can act on this particular box. For example, the pull force, then there's a friction force opposing the motion of the box, there is the weight of the box because this particular box has got mass and therefore is being pulled downwards by the earth, and there is the reaction force, the normal force which the surface exerts on the box. So these are the forces which we can identify. Our interest is to find a resultant force along this horizontal direction and also along the vertical direction. That is our interest in this case. We want to find the resultant along the vertical. We want to find the resultant along the horizontal. Are we clear? Are we clear? Resultant means that we will add the forces acting along the horizontal, we will add the forces acting along the vertical. Okay. So if we choose this left hand side, which is the direction in which the box is going to move, or if we choose the positive x-axis, which is the box moving in this particular direction, to be our x direction, positive x-axis, it means that any force pointing in this direction is going to be a positive force. If this is our positive direction, then this opposite direction, which is the negative x-axis, is going to be a negative direction, and any force pointing in that particular direction will be treated as a negative force. So our pull force in this case, or push force, is going to be a positive force. Then our friction force here is going to be a negative force. Similarly, we can apply the same logic in the vertical direction here, any force above the surface, that will be treated as a positive force. So our force pointing above the incline, which is the normal force, is going to be a positive force, and any force pointing below is going to be treated as a negative force. Now, if you have a box lying on a surface like this, what you're hoping is that this box does not sink into this particular surface. So from the word go, whatever the resultant force is along the vertical direction does not make the box change its velocity. Okay. So with that choice of forces, we start by working out the resultant force in the y direction. So we have chosen forces pointing above the incline to be positive. So in that case, our normal force is going to be a positive force. So we write it as plus Fn, then plus the force pointing below the incline, which is the weight of the box, that is assigned as a negative force. So our resultant force along the y direction is going to be Fn plus minus Fw. Fn plus minus Fw. So this is the resultant force. The reason why it's like this is because we chose, say, any force pointing in the positive y direction will be positive, any force pointing in the negative y direction is going to be negative. So in our diagram there, our normal force is pointing in the positive y direction, so that's a positive force. Our weight is pointing downwards below the incline, so that's a negative force. So our resultant force along the y direction, which is sum of the forces along the y direction, is going to be equals to this Fn. Fy is equals to Fn minus Fw. So this is the resultant force. The resultant force is a result of the normal force minus the weight of the box. This resultant force, when you're working out a resultant force, it can be positive, it can be 0, or it can be negative. So all sorts of things can happen with the resultant force. Your resultant force can be a positive value force, or it can be a force which doesn't exist. In that case, your resultant force is a 0, and your resultant force can be negative. Okay. So after we find the resultant force here, we next apply Newton's second law of motion along the y direction. So Newton's second law of motion says that the resultant force, which is this one, is equal to the mass of an object multiplied by the acceleration of the object along that particular direction of interest. In our case, we are interested in the y direction. So this part here, this is the resultant force, which you have found as Fn minus Fw. Then this m is the mass of the box. Then this ay here is the acceleration of the box along the y direction. Now, it so happens when we make substitutions here, so in place of the resultant force, we write this expression, Fn, the normal force, minus Fw. So we end up having this. Fn is equals to Fn minus Fw is equals to the mass multiplied by the acceleration of the object. However, along the y direction, on this surface, this horizontal surface which I've looked at, the box doesn't move along the y direction. In this particular diagram here, this box does not move along the y direction. It does not gain height, it does not lose height. So there is no change in the position of the box along the y direction. Since there is no change in position, then we see that the acceleration, if it doesn't move along the y direction, then the acceleration of the box along the y direction is equals to 0. Huh? What do you want?
Slack.
So the acceleration of the box along the y direction is equals to 0. That's what you have here. Ay equals to 0 meters per second squared. Okay. So we substitute this value of acceleration here. When you do that, we end up having Fn, which is the normal force, minus the weight of the box, is equals to the mass of the box multiplied by the acceleration, which is 0 meters per second squared. When we do this, clearly mass multiplied by 0, we get a 0 this side. So we end up having Fn minus Fw equals to 0. With this Fn minus Fw equals to 0, when you take this minus Fw to the other side, you end up having Fn equals to Fw. So what you see here is as follows. The conclusion we make: whenever you have something seated on a flat horizontal surface, and that particular something is not sinking or not flying off, the conclusion we make is that the weight of that particular object you have on a table or you have on a desk, the weight of that object is equal to the normal force. That is the conclusion you draw here. The weight of the object, Fw, is equal to the normal force. So always, as we have seen from our diagram, the weight is pointing down, the normal force is pointing up. So these two forces, Fn and Fw, these forces are opposite. But they are more than that. They are opposite and they are equal. Are we clear? These two forces are opposite and equal to each other. This is basically a consequence of Newton's third law of motion. So what is happening is that the mass of the box is exerting a weight on the floor. The floor is not happy about this, so the floor pushes back with an equal but opposite force. Are we clear? The floor or the table will continue trying to do this. It will continue to match the weight. However, if the weight increases too much, you will agree with me that at some point, if you keep on adding things on your table, then the mass, the weight you have on the table is more than what the table can support, then your table is going to break and things are going to move down. Okay, so this situation is only valid when your acceleration is equal to 0 along the y direction. Are we clear? So the first conclusion we make is when you put a mass on a flat surface, the first conclusion we make is that when you put a mass on a flat surface, that particular mass will exert a weight on that flat surface, but that flat surface will not sit idle. The flat surface will push back against that mass with an equal but opposite force. Are we clear? This is the first conclusion we draw from applying Newton's second law of motion. Are we clear? Hello? Is it clear? Okay. The next thing is we are done with what's happening in the y-axis. We move to what's happening along the x direction or in the horizontal direction. So in the horizontal direction, we have said that we choose the direction in which the box is going to move. So most likely, since the box is being pulled in this direction, to the left, to the right, we choose this direction, which is a plus x direction, to be positive. So any force pointing in this direction in which the box is moving, we treat that as a positive force. Then any force pointing in the opposite direction, we treat that as a negative force. So in this case, the pull force F will be positive, then the friction force here is going to be negative. So when we do that, using these two forces F and FF, we can find a resultant force along the x direction. So along the x direction, our resultant force Fx is going to be equal to the pull force F plus the friction force which is pointing in the opposite direction. So F plus minus F friction. So this is going to give us the friction, the pull force minus the friction force. Are we clear? So this is the resultant force along the x-axis. It is made up of the force which is pulling the box minus the force which is opposing the motion of the box, the friction force. So with this resultant force, we can investigate what's happening to the box. Now there are a couple of ways our box can behave along the x-axis. The first way the box can behave along the x-axis is that the box can choose to remain motionless. So the box can just stay there without moving. The other way the box can behave is that the box can move at constant velocity. Like this. So the box can remain motionless, or the box can move at constant velocity. Another way a box can move is that it can move faster, or it can move slower. Okay? So all these are different ways in which our box could move. It can choose to remain there, you leave it, then you find it there the following day. Or it can choose to move, but moving at constant velocity. Or it can move faster or move slower. In the first two cases where the box remains motionless or the box moves at constant velocity, in these two cases the acceleration is equals to 0. So when the box remains motionless or the box moves at constant velocity, in these two cases the acceleration along the x direction is equals to 0. If your box moves faster or it moves slower, it moves faster or it slows down, then there's acceleration there. If the box moves faster, then it means that the acceleration is positive. If the box moves slower, then it means that the acceleration is negative. So the first case we're going to look at is when the box remains motionless. So if the box remains motionless, it means that there is no acceleration. Okay. If the box remains motionless, then it means that there is no acceleration. We have found the resultant force along the x direction. It's F minus FF. So with this resultant force and the fact that the acceleration along the x direction, if the box remains motionless, is equals to 0, then we can write Newton's second law of motion. So in this case, the resultant force is equals to the mass of the box multiplied by the acceleration. The resultant force, which is this, is what we have here, which is F minus FF. The pulling force minus the friction force, that's what we have here, equals to the mass of the box multiplied by the value of acceleration. The acceleration in this case is equals to 0 meters per second squared, like that. So the mass multiplied by the acceleration gives you a friction which is equals to 0. Sorry, gives you a mass times 0 gives you a 0. So we end up having F minus FF, the pulling force minus the friction, is equals to 0. So we end up making the following conclusion, that in this case, our pull force, F, is equals to the friction force. This is the conclusion we make. Now, this friction, to be specific, the friction we are talking about here is the friction associated with a body which is not moving. That is what is called static friction force. So in our case here, the pulling force is equal to the static friction force. And how do we get static friction force? Static friction force is equal to the coefficient of static friction multiplied by the normal force here. The normal force, we have just seen up here that the normal force is equal to the weight of the box, always. The normal force of a surface is always equal to the weight of that particular. The normal force exerted by a surface is always equal to the weight of the object on that surface. So in this case, our normal force is equal to the weight, which is equals to mg. So our friction force will in fact become mu s, which is this, mu s multiplied by the weight. So this is our friction force. And we've seen that this friction force is equal to the pulling force. So basically, this is the conclusion we make here, to say When you try to pull an object, you have an object lying on the floor, then you try to pull it or you try to push it, but it refuses to move. The reason why it's refusing to move is because the force you are pulling with is equal to the friction force. So if the pulling force is equal to the friction force, then you don't get any acceleration. Without acceleration, then in this case, the object remains where it is. Are we clear? So this is what we have. So the pull force, if there is no acceleration, is equal to the coefficient of friction multiplied by mg, which is just the weight of the box. The other case you can have is that when you pull this box, you actually manage to pull it, so it moves. However, the box moves with a constant velocity. So if the box is moving with a constant velocity, then it means that, again, the acceleration along the horizontal direction is equals to 0. So whether the box is moving or not moving, the resultant force is still the same. It is equal to the pulling force minus the friction force. So this is Newton's second law of motion. We write it here. The resultant force is equal to the mass of the object multiplied by the acceleration. So in this case, the resultant force is the pulling force minus the friction force equals to the mass of the objects multiplied by the acceleration, which is equal to 0 meters per second. In this case, as much as the acceleration is equal to 0 meters per second, our box is actually moving, but it is moving with constant velocity. So when you multiply this mass, multiplied by the 0, we end up with the 0 this side. So we end up having F with the pulling force minus the friction force is equals to 0. So in this case, we end up having the pull force is equals to the friction force. Something similar. So this equation 24 is similar. This equation 24, the pull force is equal to the friction force, is similar to equation 19, basically identical. The only difference is the type of friction which is involved. Now our box is moving. So the friction associated with a moving object, that is what is called kinetic friction force. So this friction force, when our box starts moving, but it's moving with constant, whenever something is moving, it has got friction associated with it, and that friction is what is called kinetic friction force. So in our case, the kinetic friction force, mu Ff, is equal to the coefficient of kinetic friction multiplied by the normal force, and this is what we end up having. The normal force we know is equal to the weight, which is equal to the mass multiplied by acceleration due to gravity. Therefore, our friction force, our pull force, is going to be equal to mu k multiplied by mg. So this is what the pull force is going to be equal to. Your pulling force is going to be equal to the coefficient of kinetic friction multiplied by the weight of the object. Now, the pulling force when your object is moving looks similar to the force when your object is not moving. The difference here is this coefficient, the coefficient of static friction. In 22, so equation 22 has got a coefficient of static friction. Equation 27 has got a coefficient of kinetic friction. The coefficient of static friction is always greater than the coefficient of kinetic friction. The coefficient of static friction has got values up to somewhere 0.8, 0.7, 0.8, 0.9. That's a coefficient of static friction. On the other hand, the coefficient of kinetic friction, you'll be given a value of 0.2, sometimes 0.3. This is the reason why when you are pushing an object which is already moving, it's easier to push than when you're trying to push an object which refuses to move. If an object is not moving, then you try to push it, it is more difficult than pushing an object, that same particular object, once it starts moving. The reason is because the coefficient of kinetic friction is always less than the coefficient of static friction. Okay, so that is what happens when your object is not accelerating. So if your object is not accelerating, the first thing along the x direction is that your pull force is equal to the friction force. So it depends. Is the object motionless? If the object is motionless, then your pulling force is equal to the static friction force. If your object is moving with constant velocity, then your pull force is equal to the kinetic friction force. Another case you can have is when your object moves faster, meaning that the velocity of your object increases, or when your object slows down, meaning that the velocity of your object reduces. In both these cases, if this happens, there is a value of acceleration. So if an object moves faster or if an object slows down, there is acceleration involved. And we want to find this acceleration. There is acceleration involved and we want to find this acceleration. The reason why we want to find the acceleration is because once we know the acceleration of an object, we can predict what its velocity is going to be after a certain amount of time. We can also predict how much distance that particular object has moved after a certain amount of time. So only if we know the acceleration can we actually try to behave like physics people, where we are predicting, oh, after this amount of time, this object should have this much velocity and this object should have covered this much amount of distance. So that can only happen if you know the acceleration. In our case, we can find this acceleration from applying Newton's second law of motion, this along the x direction. The reason is because we already have a resultant force. The resultant force along the x direction is the pull force minus the friction force. So this we already have. If we want to find the acceleration, then the only thing we need to do is we need to make the acceleration the subject of the formula by dividing on both sides with the mass. And that's exactly what we do. So here we have the pull force minus the friction force equals to the mass of the object multiplied by the acceleration. So once you have a resultant force, what you're interested in finding is the acceleration. So the acceleration AX is going to be equals to the resultant force, which is F minus FF, divided by the mass of the object. This is what we use Newton's second law of motion for. We use it for finding acceleration if you know the resultant force, if the resultant force is present. So if the resultant force is present, then you can use Newton's second law of motion to find the acceleration of that particular object. How are you going to know that the resultant force is present? You know that the resultant force is present if the object moves faster, meaning that the velocity of that particular object increases, or if an object slows down, meaning that the velocity of that object reduces. That's how you know that the resultant force is present. A resultant force causes the velocity of an object to increase or the velocity of an object to reduce. So once you see an increase in velocity or a decrease in velocity, you need to work out the resultant force. You need to identify which forces are acting on this particular object. So in this particular case, we have a resultant force. The pull force minus the friction force divided by the mass gives us the acceleration of the object. Like that. So it depends. If the pulling force F is greater than the friction force, if F is greater than the friction force, if this F, the pulling force, is greater than the friction force, then F minus FF is going to give you a positive resultant force. With this positive resultant force, you divide it by the mass, you're going to get a positive value of acceleration. If your acceleration is positive, it means that your object's velocity will increase with time. So your object's velocity will increase with time and your object will move faster and faster. In the case where the pulling force is less than the friction force, if you have such a situation where the pulling force is less than the friction force, you can see that the resultant force in that particular case is going to be negative. When the resultant force is negative, you divide this negative resultant force by the mass, what you get is a negative acceleration. So this negative acceleration will slow down your mass until it comes to a stop. What is actually more common than having a force which is less than a force than a friction is actually having no pulling force at all. So you can have an object which is moving, but there is no pulling force. And that happens when an object is sliding on a flat surface. So when your object is sliding, there's no one who is pushing it, or there's no one who is pulling it. In that case, when you've got a sliding object, the pulling force is equals to 0. So when the pulling force is equals to 0, when this guy becomes equals to 0, what you end up with is minus friction force divided by the mass. So when you look at this, the acceleration along the x direction in this case is going to be equals to minus the friction force divided by the mass. This will give you a negative acceleration. Eventually, with a negative acceleration, whether you like it or not, when an object is sliding, it doesn't matter how smooth the surface is. When an object is sliding, because of this, that particular object eventually will slow down and will eventually come to a stop. Are we clear? Is it clear? I'm not getting any responses. I don't know why, but good. Okay. So, when an object slides, there is no force pulling it. So the pulling force in that case, which I found here, this F, is going to be equals to 0. So the only force which is going to be working on the object is going to be the friction force. This friction force will result in an acceleration which is negative. A negative acceleration will cause your box to come to a stop eventually. So once you know the acceleration that is negative, then you know the initial velocity. If your box is going to come to a stop, then the final velocity is going to be 0. So you know what the initial velocity is, your box comes to a stop, you know the acceleration, you can find out what the stopping distance is supposed to be. So that is a question which is usually asked. We ask you to find the stopping distance, or we ask you to find the friction force when we give you a stopping distance. Okay. The other case, which is also very common in first year physics, is when you have a mass supported by a rope, as in this case here. You have a mass, this box here, instead of it being on a flat surface, now we hang this mass from a rope. So we hang this mass from a rope like this. This mass has got weight, so the weight of the box is pointing down. Now, the only thing stopping this mass from going down is the force which exists in the rope, or in the string we have tied the mass to. The force which lives in the string, that is what is called a tensile force. So when you have a string or a cable or a thread supporting a mass, there is a tensile force in that particular mass, in that particular rope. So that rope, depending on the material the rope is made up of, if it's made up of nylon or rubber or whatever it is, or cables, there is a force which lives in that particular mass. Sorry, in that particular rope. Okay. And if this box does not move, so this box can either choose to move or it doesn't move. It can stay there the whole day. If it doesn't move, then the box has chosen to remain motionless. The other case is the box can be lowered down slowly, or it can be lowered down faster. If you lower the box slowly at constant velocity, so in that case also you don't have any acceleration along the y direction, or you can lower the mass fast such that the velocity of the mass increases. So in that case, you have got acceleration. Either way, as you can see, there are only two forces acting on this box. One is acting downwards, the other one is acting upwards. There is no force along the horizontal acting on this particular box. So the resultant force in this case is only a result of two forces, the weight and the normal force. So the next thing you have to do if you're going to work out resultant force is you need to choose directions. Which direction is positive? Which direction is negative? Now, if this rope cuts, this box is going to move down. Without this rope, the box always moves down. The box is not going to move up. So as much as the tension is pointing up, naturally the box has got a tendency to move down. So in that case, my advice is choose the direction in which the object is moving to be positive. Okay? Choose the direction in which the object is moving to be positive. So in this case, since the box will tend to move down, I choose the weight of the box to be a positive force, and I choose the tension to be a negative force. It is up. This is my advice. This is something which I find simple, so that when your answers come out, your answers make sense. Choose the direction in which the box tends to move to be a positive direction. So in this case, the weight of our box will be positive, then the tension in the rope is going to be a negative force. So when you do that, we can work out the resultant force along the y direction. So the resultant force along the y direction in this case, resultant force along the y direction is going to be equal to the weight of the box, Fw, plus the negative tension, which is pointing up. So here we have Fw, which is the weight of the box, is positive because we have chosen the direction in which the box will move to be positive. So the tension is pointing in the opposite direction. So in that case, our tension is being negative. So the resultant force here, Fw, is going to be equal to the weight of the box minus the tensile force. So we have a resultant force along the y direction. With the resultant force, the point really is, the reason why you're finding resultant force is because you know resultant force is connected to acceleration and the mass of the object through Newton's second law of motion, which is this one. This is the resultant force is equal to the mass of the object multiplied by the acceleration of the object. That's why you're interested in resultant force. So in this case, if our mass remains motionless, that's one thing which can happen. It just stays there. So in that case, the acceleration is equal to 0. Or our mass can be lowered downwards at constant velocity. So if our mass is lowered down at constant velocity, again, in that case, the acceleration is equal to 0. Or our mass can accelerate much, much faster downwards. So in that case, you have good acceleration. So we look at these cases in order. So if our mass remains motionless, then our resultant force, which is this one, the weight of the box minus the tensile force, is equal to the mass of the box multiplied by the acceleration, because our mass has remained motionless. It's being supported by the rope. So this m multiplied by the 0 gives us a 0. Then we end up having this, the resultant force, which is the weight minus the tensile force, equals to 0. So we end up having, we draw the following conclusion, that the tensile force is equal to the weight of the objects supported by the rope. And this is always the case. The weight of the objects you hang on that particular rope, if that object doesn't move, will cause the rope to generate a force which is equal but opposite to the weight. So the tensile force is always equal to the weight of the object. Are we clear? Again, this is an application of Newton's third law of motion. Okay. If, on the other hand, our mass is lowered down, it moves, but it's lowered down at constant velocity, then in that case, again, the acceleration AY is equals to 0 meters per second. So if the acceleration is equal to 0 meters per second, then we can make substitutions in Newton's second law of motion. We know the resultant force is the weight minus the tensile force equals to the mass of the load, block, or whatever it is, multiplied by the acceleration, which is 0. So Fw minus Ft equals to the mass multiplied by the acceleration, like this. So we end up having Fw minus Ft equals to 0, and in this case, again, the tensile force is equal to the weight. So if you lower a mass, you have a mass supported by a rope, then you lower it down at constant velocity. So in this case also, the tensile force, the tension generated in that rope, will be equal to the weight. Are we clear? Okay. The last but not least is when you have an acceleration. When your mass is lowered down very, very fast. When you lower your mass down very, very fast, in that case, you will have acceleration. So when your mass is lowered down very fast, then you are going to have acceleration. Or when you lift your mass very fast, then you're going to have acceleration in that case. So in that case, we have a resultant force, which is the weight, Fw minus Ft, equals to the mass multiplied by the acceleration. Now, whenever there is acceleration, your interest is to find out how much is this acceleration, so that you can predict how far this thing is going to fall within a certain number of seconds, or how much distance is going to fall through in a particular number of seconds. So that is a reason why you find acceleration. Acceleration allows you to predict what will be the velocity after a certain number of seconds, or how much distance or displacement or height through which this particular mass is going to fall. Once you have your acceleration, all that becomes very possible. Okay. So in this case, the resultant force, which is Fw minus Ft, is equal to the mass multiplied by the acceleration. What we want is the acceleration, Ay. So we divide both sides by m. So when we divide throughout by m, we end up having Ay is equal to the weight of the box minus the tensile force divided by the mass. This is going to give you the acceleration. Are we clear? So this gives you the acceleration with which that particular mass is being lowered down very, very fast. So we have come to the end. Do we have any questions?
Yes, I have a question.
Yes, go ahead.
So, for the equation that you've written, A1 is equals to Fw minus Ft over N. Do we consider the same Ft, the tension force for the object when it is at rest, or what?
No, when you are lowering down something, when you are lowering down something very fast, usually the tension is less than the weight. So when there's acceleration, usually something is less than the other.
Okay.
Yeah. I don't know if you have tried to lower something down fast. So usually you don't hold the rope so tightly that the tension increases. You kind of let, otherwise if you do that, then you end up having no acceleration. So usually when there's acceleration, when you lower your mass very, very fast, okay, the tension in the rope reduces. Any other question?
It's clear, sir.
Okay. Any other question? Is there any other question? Lombe, yes?
Yeah, but when something's like
When something is what?
slide when no force is being.
Yes.
When something slides, I wasn't sure about what you said.
Oh, so when an object is sliding, there is no pulling force
Not
because
clear about what you said when something slides.
so the acceleration along the x direction in our case was this one. Ax is equals to the pulling force minus the friction force divided by the mass. Okay, so if the pulling force is greater than the friction force, then your resultant force is positive, and you divide the resultant force by the mass, you end up having a positive acceleration, which will result in the velocity of your object increasing. However, when something is sliding, that happens when the pulling force is equals to 0. So when you've got a sliding object, then the pulling force is equals to 0, like this. So the only force present when an object is sliding is the friction force. So this F is equals to 0. You put a 0 here minus F, you end up having this. So you have a negative here, negative friction force divided by the mass. So this negative friction force divided by the mass is going to give you a negative acceleration. When you get a negative acceleration, it means that the velocity of your object, which is sliding, is going to slowly reduce. It can slowly reduce or it can quickly reduce. But the whole point here is that the velocity will reduce because of that negative acceleration, and eventually your sliding object, whether it likes it or not, has to come to a stop. So you can't slide forever. You have to come to a stop. No matter how smooth your thing is, you can't slide forever. Are we clear? Any other question? Okay, if there are no other questions, we'll stop here. The lecture, as usual, was being recorded. So we'll upload the recording to YouTube, and later on, we'll post the recorded recording into your Moodle so that you can watch the video, the recorded lecture at any other point during the course of the year, or when you're revising for your exams or your tests or anything, whatever it is. Okay, so I'll see you on Thursday in the morning when you're looking. We are going to look at the motion of an object on an incline. So unless there are any other questions, we'll stop here today. Okay, I'll stop sharing. Okay, so see you on Thursday.